So let me just see. Can you see the slides? Is it visible now? Let me try this again. Hang on. Okay. Is it visible now? Great. Okay. So good evening, everyone. Assalamualaikum. And first and foremost, I would like to thank the organizers for inviting me to give this talk. This is the first time I've given a talk sort of virtually to another university. So let me just close this. Okay. So the title was actually given to me by the organizers, which I agreed, of course. It's about mathematical physics. Partly, suppose I graduated from a program on mathematical physics, I guess, and also I've actually taught some courses on that. So let me move next. So what, oops, sorry. Okay, can you see this? Right. So what is mathematical physics? Well, some people think that, okay, mathematical physics is essentially just like applying maths to physics. In a way it is, but it's really a kind of a hybrid situation where, if you think of it, it really lies in between maths and physics. And this is the way we see this is essentially we look at for example, the physics classification system and also the maths classification system. So there are available physics application system known as PACS. This was the old one, which is essentially physics and astronomy classification system, and is listed under mathematical methods in physics. There's a new one, which is its acronym is PHYSH, which is stands for Physics Subject Heading. And you can, I think, let me just see if I can use my tablet. Right, you can see that over here. Okay, so essentially it is in the physics classification system as well as the maths. So in the maths, we have what we call, try to adjust this, okay. In the maths, they have this mathematics subject classification, which is the latest one is 2020. The one who actually is responsible for this classification is the one given by Mathematical Reviews and ZB Maths, which is based in Germany. So these are the codes, essentially. It begins for the physics case, the one that's related to physics begins with 70 until 86. The one that will probably concentrate most will probably 81 until 83, okay? So this is essentially most of the modern physics where they are, okay? The rest is probably, slightly more classical in a sense that it exists before the 20th century. And you can actually check this what you call mathematical subject classification at this particular URL. Okay, and here is the map of mathematics. Not sure whether it's visible or not. Do you want me to enlarge this? Let's see. So let me just go back to the previous slide. So we had this classification where the one that I will be concentrating on will be the quantum theory, statistical mechanics, and relativity and gravitation. So let's see where they are in this picture. Here you have quantum theory here. And now where's the relativity? Let me see, it must be somewhere close. It's global analysis here, and then I think it should be close here, but never mind. So quantum theory is part of the mathematics classification, and all these links essentially is like a cross listings. So that means quantum theory is actually interacting with some other fields of subject of mathematics. So this is statistical mechanics. And then there should be relativity somewhere, which I cannot find at the moment, but never mind. Okay, so in other words, all these links tells there's some connection in terms of when people write papers, they try to classify what subject heading that it should have. Okay, so the more the more papers that links between two subject headings, okay, the thicker the line is. And you can see, for example, over here, this is relativity. Okay, so you can see there's a thick line between quantum theory and relativity, for example, and also a thick line with other subject. I'm not sure what this is. This is probably structural matter or statistical mechanics. Okay, so but you also have all these other links, which we will try to mention this again at the end of the talk. Okay. The mathematics subject classification sort of emphasis more on the maths. So we're going to go to a different map. Okay. I believe you have seen Archive before. Archive is a preprint server. So, and they have subject headings. And mathematical physics essentially are categorized under both maths and physics. So you can see over here, it's given in blue because it's supposed to be more under the maths compared to physics. Okay, so you can see mathematical physics is a sub topic inside the maths category. And you can see all the other physics topics in purple here. The blue ones are actually the ones being classified under the maths category. And I think this is probably computer science or something. Okay, so in other words, there are a lot of connections between each other. Okay, and the thicker the line, you should see as something which is more interacting with the other subjects. Okay, so we're going to return again to this map of mathematics later on. So what is mathematical physics per se? Maybe I should remove this. So, well, mathematical physics is already a subject. Most universities that offer physics program would actually have at least two courses that can be categorized as mathematical physics. In UPM itself, we have this subject called mathematical methods in physics, okay, and the other one would be mathematical physics itself, okay. But really, these two subjects are sort of related to each other, and I could have called this mathematical methods in physics as mathematical physics 1, and then you have mathematical physics 2, or I can simply say that, okay, I have mathematical methods in physics, and the mathematical physics is mathematical methods in physics 2, okay. So, and what the courses actually contain, it's almost anything that you need for undergraduate, the maths tool that you need for undergraduate physics program. Okay, so you can think of all the possible mathematical tools that usually used by undergraduate physics. They are all contained inside these two courses. So you can think of the whole of mathematics. You try to condense it to two courses. Now I've talked to students, and they say that this is probably one of the nightmarish kind of subject, because it's like learning all of the mathematics into two courses, okay, condensed, okay. But it's not only nightmarish to students, but also to those who design it, okay, and to those who teach it, because there is a lot of ground to cover, okay. So, for example, in UPM, for example, we are using Bowers most of the time, and sometimes Riley and Hobson and Benz, okay. And what we do between these two subjects, okay, we sort of divide the book into two parts, and then the first part will go to the first course, and the second part goes to the second course, okay. And one of the difficulty with teaching this particular subject is essentially it's because it's a mixture of different mathematical topics. You tend to have it a little bit incoherence in some sense. But can you actually put this subject to some kind of whether there's a kind of theme running through all the topics inside this particular course? I think the most favorite sort of thematic idea that can run almost through all the topics essentially is the idea of linearity and linear spaces. So this will include all the vectors, the matrices, and solutions of ordinary differential equations. Okay? So all it needs just to behave to behave accordingly to linearity of the, in this case, for example, here, linearity of the solutions, for example. Okay, so that sort of runs through for vector spaces, matrices, operators, and then your differential equations. But of course, there will be some subtopics will be slightly off, like integration and things like that. So that's a bit, sort of added subtopics to that theme. Okay. Now, how do I find? Now, I'm also a student at one point in time, and still a student. Okay, I'm still learning. Here's my learning experience. My first mathematical physics undergraduate course, was taught by Professor Green. Professor Green is the person in this picture, okay, in the center there. He's a well-known mathematical physicist in Australia, simply because his ideas are very original, and then he's also a student of Max Born. I think everyone knows Max Born, who actually gives the probability interpretation for quantum theory. Okay, and the rest, I think C.A. Hurst, Charles Hurst is there. Not quite in the picture is Lindsay Dodd. This is my project supervisor. Okay, undergraduate project supervisor, and Peter Zacharias is here and here. Okay, so there are only 4 academic staff inside that department. Occasionally, they will invite people from a different university to also teach the mathematical physics course. Okay, so there are essentially Professor Green taught me a course called Mathematical Methods, okay, which is highly original. Okay? One of the things that I experienced with Professor Green is that when I look at his notes, the one that I took from his lectures through what in that case Blackboard, those days, okay. I'll try to find some books to refer to, and I could not find anything which is similar to what he's doing. So he's pretty original. So some of the things that was covered by Professor Green in mathematical methods, and that's the first course. Okay, you have to remember there are 2 different courses: mathematical methods and mathematical physics. The second one is supposed to be more advanced. He actually introduced the idea of reference frames, those in the beginning for the mathematical methods, and also the transformation between reference frames, which is in that case was a group called GLN. And that was not quite common in a sense because GLN normally introduced in a different course. So it was quite a challenge, but one of the things that it made me appreciate that I have to really think for myself because I couldn't find any books that actually can help me through the course. Okay, so that was the good thing about having this original thinkers. Okay, so Zacharias is my lecturer for general relativity and special relativity, and he actually wrote a nice book, a course in modern mathematical physics, which introduces, if you can see the picture here, introduces groups, Hilbert space, and differential geometry for that, if you use this particular reference book. And this reference book is meant for undergraduate. Okay. So you can see how much at once they are teaching their students. Sorry about that. So what else I wanted to say? Yeah. Let's prove. So you can have a look at how the Adelaide in those days, what kind of things they are teaching the students. I used this book at one point in time for UPM for a graduate course rather than an undergraduate course because it involves a lot of different things. Okay. Right. Now, here's the part where I'm supposed to tell you what is the difference between mathematical physics, theoretical physics, or even applied maths for that matter. Okay. Well, as I said, mathematical physics sort of sits in the middle, really sits in the middle between the mathematics category and the physics category. Even the mathematicians recognize this, and the physicists also recognize this. Okay, so one of the questions that I always get when I headed when I was in the Institute for Mathematical Research, most of the other what you call researchers are from the mathematics department. So they start to ask me, isn't mathematical physics just applied maths? Well, I sort of, okay, if that is so, why then there's a department of applied maths and theoretical physics in Cambridge. So this is where I had lectures here. This is the old the MTP, they call it. This is the one in Silver Street. Okay, So they have all the giants inside there, including Stephen Hawking. Okay, and the idea here is essentially that different applied maths and theoretical physics, in a way, there's a kind of uh, differentiating the tools that's being involved. The applied maths courses contains a lot of differential equations, whereas for theoretical physics, it intends to cover almost any other subjects of mathematics. So it involves other mathematical structures. Okay? So, and you might say that, oh, well, that's because you have applied maths and theoretical physics. It's not mathematical physics. So what's the difference between theoretical physics and mathematical physics? Well, essentially, mathematical physics can be considered as a subset of theoretical physics. Okay? Where the only difference, if you want to what you call push for the difference, the only difference would be mathematical physics are being more rigorous in terms of the kind of maths that's been used. Okay? Theoretical physics tend to be a bit more conceptual in some sense. If I want to give a kind of, so what you call percentage of difference, maybe theoretical physics will have less, maybe something like 30% of maths is being used in theoretical physics, but you have 60% actually being used in mathematical physics. Okay, so it's being more rigorous. Now, I also encountered a different, what I call label, if you want. Okay, so you have this essentially the Babel, okay, mixtures of different ideas, which is called physical mathematics. Somebody threw to me when they wanted to de-emphasize physics in the Maths Institute. They suggest, okay, let's have physical mathematics instead of mathematical physics. The idea is essentially the first word is supposed to be an adjective. And the second word is supposed to be the base. So in this particular case, the base would be mathematics. In mathematical physics, the base would be physics. Okay, so in that sense, I can understand why they try to suggest this idea of physical mathematics. But there is a new idea that is actually initiated by Greg Moore, saying that, okay, the difference between physical mathematics and mathematical physics is that physical mathematics is actually contained, is a subset of mathematical physics, and the way it's been differentiated or identified is the kind of maths being used is actually comes originally from physics. And you might say that, okay, mathematical physics might have that. So that's why it's actually contained here. So one of the things that Greg Moore is actually a string theorist. And you can see that a lot of these string theorists actually create new mathematics, okay, which was not there before. So in other words, the new maths is like, if you want to make it a bit more clear in terms of the differentiation, mathematical physics tend to use known mathematical tools, whereas physical mathematics tends to create new mathematical tools. So this is perhaps the kind of justification Greg Moore was trying to bring up this idea of physical mathematics. For me, I'm a bit uneasy about physical mathematics. I can understand mathematical physics because you can talk about physics which being formulated in a very mathematical way. But if you talk about mathematics being physical is a bit odd. Okay, so that's my personal opinion, of course. Right. So here are an interesting question is, when is the first time that mathematical physics being used in the literature, the term mathematical physics itself? It was actually, there was a book called Mathematical Physics, Mathematical Principles of Natural Philosophy. And this was actually written by John Harapaf. It's available to see. You can see what the topics are. In fact, the topics that's involved is essentially heat, gas, elasticity, and gravitation. Okay, and the book is published in 1847. So in other words, the term mathematical physics was already there much earlier on. Okay, and then Poincaré, which is another giant of in both the maths world and the physics world. Okay, he wrote a short book, or very thin book in this French, but it's available in the translation is now available in the Bulletin of American Math Society. It's called Present and Future of Mathematical Physics. Okay, so that was quite early. The translation appears in 2000, but the original article is actually in 1904. Okay, so in other words, mathematical physics are already in play even in early 1900s, but even earlier than that, we have 1847. There was another claim that mathematical physics terminology has been used even earlier than 1847, I think by D'Alembert. So these are the early texts, but let me go to contemporary ones, which is essentially what I think would be a good thing to have if you are really interested in what you call mathematical physics at this particular point in time. Well, there is a book called Analysis, Manifolds, and Physics. Okay, I would consider, and there are 2 volumes of it. So these are written by Yvonne Choquet-Bruhat, Cecile David Moret, and this is Margaret, sorry, Dillard Blake, and it's published in 1977, and it contains almost all of the mathematics that you need. Okay, so this was the first volume, and there's a second volume that comes out. It sort of focus more on the applications. So one of the things that we sort of played during our graduate days, PhD days, is say, find me a book that you will take to a desert island. Okay? Only that one book. Then this book was actually mentioned. Okay, and the other contemporary text that I would suggest to have for mathematical physics is the one by Isham. This is not Hisham. It's without the H bar. Okay, Chris Isham. He is my external examiner for PhD. Okay, I think the first one would be the Lectures on Quantum Theory, which is a very good book, and it's very thin. Okay, so you don't have to worry reading too much, because it's I think just 100 over pages. Okay, and the same thing for the other 2 books, Lectures on Groups and Vector Spaces, and then this one is what you call a really unique book for differential geometry. Okay? Even the experts was surprised by the clarity and also the different topics that it takes up for the differential geometry. So I really recommend those books by Chris Isham. And another book that I actually found, initially it was not published by Springer, was published by Odense University Press, which I find which is very helpful for me to understand differential geometry, is by Felsager, called Geometry, Particles and Fields, and now it's being republished under Springer. It's a good book. The other one that probably I didn't know about this book until Professor Quek from CQT in Singapore recommended me to read this book because it contains all the things that I need to know. For example, people are doing string theory, what do they do? Infinite dimensional Lie algebras. It's all covered inside this book called Mathematical Perspectives on Theoretical Physics. I have one other, what I call, favorite book of mine, which I was really surprised when I first saw it. It's by Robert Giroch. He's a relativist. And the book is simply titled called Mathematical Physics. But what he does in this book, it uses category theory to introduce all the mathematical tools. And category theory was not a popular thing, and no, it was only popular, I think, in the late 90s. Okay, and this was actually published in 1985, mid 80s. Okay, so that was I think it was an original way of representing mathematical physics. So I do recommend reading those books to really master the idea of mathematical physics. Now, let me go to why people use maths to describe physics. Well, you have this all these quotations that you probably have seen somewhere. The first one is by Einstein. In the popular literature, they tend to say the incomprehensible thing is that the world is incomprehensible. But actually, the real wording was this one. Okay, this was actually published by Einstein in Journal of Franklin Institute, and in that book, the paragraph before it was talking about how we maintain certain kind of ideas in order, and then that order is like a kind of logical sequence kind of thing, and that thing is making the world to be comprehensible to the particular scientist. Okay, and the fact that it can be done is considered as a miracle to Einstein. And then, of course, the idea of unreasonable effectiveness of mathematics was actually a title of an article by Wigner. Okay? Wigner is essentially a mathematical physicist that uses a lot of group theory, okay, for describing physics. Okay? So it says, the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in the future research and that it will stand for better or for worse to our pleasure, even though perhaps also to our bafflement to wide branches of learning. Well, this theme of unreasonable effectiveness of mathematics has been recurring. You can see even conferences takes up this phrase of unreasonable effectiveness. Okay, so but for those who are dealing with philosophy, here's one philosopher, Arizu Islami. He says that one has to be careful about this okay, the mathematical formulation of physical theory, moreover, must not be taken as a guide to its truth. Such physicist forgets what Wigner actually wrote this somewhere, what Wigner calls the nightmare of the theorists. The existence of numerous examples of theories with elegant mathematical formulation and alarming accurate description of group of phenomena which are nonetheless considered to be false. And one can see this kind of criticism is now being used against things like string theory. People are debating about whether string theory is really theoretical physics or not, things like that. But the idea is to be careful. Okay? So one should not just rely. I think Sabine Hossenfelder has also wrote a book called Lost in Maths, thinking that maths can actually guide you to the truth. Okay? So that's something that one has to be a bit more careful. Even worse is the following. Sometimes maths, usually people trust maths. Okay? So here's a piece of maths. This was actually made known to me by John Byers. You can see that this is like a repetition of integrals using different factors over here, okay, and it always gives you pi over 2, okay, and this pattern holds for n which is less than 9.8 times 10 to the power 42. That means can grow, this expression can grow very large. And you think that, okay, maybe this actually is true for all n, okay? But however, it actually fails at n greater than something 10 to the power 43. So this was surprising. Actually, this was published by two mathematicians in Ramanujan journal. Okay, and some of this has been also tried to given a physics perspective. For example, this was given a connection with the idea of a random walk problems. Okay. So you can have a look at those papers to see that these are things that one has to be really aware and be really critical when you do when you try to deduce things. Okay, now I'm getting to things which are called standards, which are aspect a good theoretical physics or mathematical physics student will actually have in the end. Okay. First, the standards from classical mechanics. Okay, here a useful principle. I'm talking here standards in the sense that these are essentially used in advanced kind of concepts for classical mechanics. For example, here in classical mechanics, the useful principle would be the principle of least action. Okay, or in a broader context, it's actually given by the mathematical topic of variational calculus. Now, why is this useful? You probably have seen the idea of action even in particle physics. So they write this, things like L equals to F mu nu, and then some other things. So this going to be integrated over time, or in this case, this should be over space and time. And this thing is called the action. And if you vary this action, okay, with respect to the variables, then you'll be able to get some equation of motion, okay? And in classical mechanics, the equation of motion will just simply give you F equals to ma. But in other cases, it gives you something which is much more general. Okay, so this is a very useful principle. Sometimes people skip this. I think this is one of the beautiful things that one should teach. Okay? The other thing, if you do classical mechanics at a higher level, then you probably have come across Lagrangian mechanics and Hamiltonian mechanics. Okay, so Lagrangian mechanics is the one essentially Lagrangian is given by t minus v, and Hamiltonian is just t plus v. And you can apply again the action principle to both formalism, and then you can get what we call the Euler-Lagrange equations and Hamilton's equations. Okay, so those are essentially equations of motion. But over there, what happened is that Lagrangian is going to be a function of, sorry, this doesn't come up well, it will be a function of q and q dot or phi and phi dot. Okay, so the variables here are position and velocities. So the state of a classical system is given by these two variables. So if there are n variables for q, then there will be n variables for q dot. So the pair of q and q dot is sometimes called the velocity phase space. Okay. And same thing for Hamiltonian mechanics. Hamiltonian mechanics uses the q and p. You have the position, and then you have what we call the canonical conjugate momenta. Okay, so essentially this q and p will form another kind of phase space called the momenta phase space. And these two phase space, because you have a pair of it, they are considered giving you an even dimensional space. Okay, the manifold is just a technical way that you have a particular kind of space with certain structures in it. Okay, and this even dimensional space is equipped with this tensor, okay, called the symplectic form. Okay. I'm not sure whether some of you might not have heard about this, but I hope you have heard about tensors. And it's not just a tensor; it should be a tensor field. And this tensor field will have to be antisymmetric. Okay, and you can put this on this space called the phase space, and they are called symplectic manifolds. And there's a whole subject called symplectic geometry. Okay. And this would be the modern way of formulating classical mechanics. There's another alternative way to describe all of these equations of motion, is just to restrict ourselves to functions and the legal algebra of functions. So we form what we call the Poisson bracket, which is really a antisymmetric product of the derivatives of functions. Okay, and a space which is equipped with this Poisson bracket structure is called a Poisson manifold. Okay, so here the slightly general thing than the symplectic geometry is the fact that it doesn't have to restrict oneself to even dimensional. Okay, what are the things that you need to know with respect to classical mechanics is perhaps the new, relatively new, it's not new anymore, the idea of nonlinear dynamics and chaos. Okay, so these are essentially a lot of experimental simulations been done with respect to this nonlinear dynamics, and they produce sometimes chaotic motion and sometimes quasi-regular kind of thing. So there are plenty of applications of this. But generally, all of this can be termed as a dynamical system. And one of my favorite book of dynamical system is written by this two person here, which is it's quite thick. I think more than 1,000 pages. So and it contains all the necessary things, mathematical tools that you need for describing dynamical systems. Before I wrote down this particular slides on relativity, there was another subject that I thought should have been put in, but unfortunately I'm not very familiar with it, okay, because I only taught the subject only a few times at UPM, for example, statistical mechanics. So there's another standard thing that you should know, which is from the statistical mechanics, and then it has also some relation to the idea of dynamical system. So this one I left out because I don't have any particular detailed experience about this. Okay. But let's talk about relativity. So the idea which is useful over here is the equivalence principle, so equivalence of different frames. And the underlying mathematics over here for special relativity, it should be the Lorentz transformation, but in general, it would be a general coordinate transformation. Okay? And in this particular case, you'll find that your space-time is described by a particular type of spaces called pseudo-Riemannian manifolds. If you have done relativity before, the idea of pseudo-Riemannian means that your metric is not, it has a mixed signature. Okay? And what you have in this particular case is all your physical quantities are going to be described by geometric things like vector fields, tensor fields. So these are defined on these manifolds. Okay? So the mathematics that you need to do all this is essentially differential geometry. There are two ways to do it. You can use local charts using local coordinates, or you can describe it sort of independently of all the coordinates. And these are normally written in terms of geometric maps. The other probably a standard thing to have, or at least for my interest, is the idea of symmetries in general relativity. There you can talk about killing vectors, killing tensors, which are essentially, you think of, for example, taking a killing vector here, take the lead derivative of some, in this case, metric tensor. So if this is equals to 0, then this is a killing vector. And you can generalize this for tensor as well. Okay? And the symmetries can also be generalized to another concept called collineations. So what happens in this particular case, instead of having the metric tensor, you can use other tensors. An example would be Ricci collineation. Okay, so this can be another tensor over here. We say, let's say something A mu nu. So this, so you study the kind of symmetries that actually arise from this particular equation. My favorite book on differential geometry is actually this book. It's a thick book, again about 1,000 pages kind of thing. Simply because it uses the idea of these global maps more than local coordinates. Most of the differential geometry that you students of theoretical physics tend to use local coordinates. So they start to do, and they are good as well. Okay? They are good because you can actually do real calculations. When you do it in terms of maps, well, it's a bit general and there's no calculation for you to check. but it gives you a much more global picture. Okay? The only thing that you need to be careful over here is that sometimes when you do all this abstract stuff, you tend to assume things. So that's the only problem with that. Okay. So I'm running out of time now. Okay. The other standards is of course high energy physics or particle physics. The useful principle over here is to use symmetries again, just like symmetries in the case of the space-time case. Okay. So we talk about Killing vectors and Killing tensors, and then collineations. Here you have symmetries to classify particles, okay, and the local symmetries to essentially tell you something about particle interactions. Okay, so the kind of maths that you need to use, okay, perhaps I should mention about the symmetries first. So they are normally described by Lie groups. These are sometimes called continuous groups. And these continuous groups can contain discrete groups. And sometimes these discrete groups play an important role. One of the quite recent idea is to consider these discrete subgroups playing some role in determining your fermion masses and mixings. Okay. So again, I've listed some references here. So my favorite book for, no, a very introductory book is essentially Naive Lie theory. There are other books like Gilmore that you can actually try to use for group theory. What else? And of course, gauge theory is perhaps the most friendly gauge theory books is essentially by Bias. These are essentially, these books are old books, but these are the ones that I've used during my graduate days. Okay. All right. Finally, my favorite topic for the day, quantum theory. Okay. Over here, oh, I should, since I put pictures, I didn't explain why this. This is from, I think it was 60 years of Yang Mills. And I had the good fortune to be sitting here representing Malaysia. This is a kind of forum, okay? And I don't know if you can actually notice over here, this is David Cross. So when I first was told that I had to sit together with David Cross is a novella, right? So I was scared to death. And then there's another Thai person sitting next to me. He was also saying, I would stay quiet most of the time. Of course, we speak about our own countries and so on. Okay, going back to quantum theory. So quantum theory essentially is not readily available. So normally what people do is they have classical theory to begin with, okay? And then when they have a classical theory, then they try to construct a quantum theory out of the classical theory. And that process is called quantization. Okay? The idea is to turn what we call classical observables, which are just functions, for example, the Hamiltonian, for example, okay, to self-adjoint operators. So this will be a quantum observable. Not only that, we also need to change, previously, this is the reason why I started off with classical mechanics. We also need to change, say, the Poisson bracket, okay, to commutators. Okay. So these are the standard thing that one needs to do, and you have to do this for different physical systems. Normally, the standard quantum mechanics that you find in the books are what we call quantum mechanical systems on linear spaces. Okay, on vector spaces. Your Rn, for example, is a vector space. But one need to be able to generalize this to different spaces, which is not linear. So this causes a problem with respect to how to do the quantization. And there are several different quantization routes. The one that I like most is the one that emphasizes global properties. So in this sense, if you emphasize global properties, then it needs geometry. Okay? And the geometry will somehow intertwine with symmetries. So geometry, so here is group theory. And there is one particular program, one particular approach is the canonical group quantization. Okay? So what does it do? If you think what happens over here, this is sometimes called a CCR. Canonical commutation relation, which is a Lie algebra. Okay? So what Chris Isham do is to say, okay, Lie algebra works at the local level. So we need to upgrade this to the global level. And the connection here, Lie algebra will have a Lie group. Okay? So it uses the Lie group as a global perspective of the algebraic commutation relation. Okay? And this can be done in a way that one takes into consideration of the global properties. Okay? So for example, if we do, say, quantization of a particle on a circle, then you know that if you use this commutator, then it's going to give you wrong answers. So these are things that requires you to need a little bit more mathematical sense before you can actually try to do this. So what else in quantum theory? So let me show this picture. This is me, my younger me, okay, here, and this is Chris Isham. Okay, what else that one does in quantum theory? Well, there are the new things that you heard in most of the popular literature. We talk about quantum information, quantum computers, quantum communication, and these are just direct applications of quantum mechanics. Okay, so but of course you can make it a bit more complicated. What I'm doing with my students at the moment is to look at geometric properties of quantum information. Okay. So I think I'm reaching the end. Here's a conference that was, let me check. The conference was something in 1990 something, I can't remember now. The conference was actually organized by Professor Lim Swee Ching, and he invited over Cecile DeWitt Moret. Remember, Cecile DeWitt Moret was one of the authors of the book that I mentioned, It's Good to Bring to a Desert Island. After this. Yeah, yeah. Cecile DeWitt. Cecile DeWitt actually is the wife of Bryce DeWitt. Bryce DeWitt is the one of the pioneers in quantum gravity. Okay? So Cecile DeWitt was given the task by the organizers of the conference to talk about mathematics in quantum theory. I'm not sure you can see the text over here. Let me try to enlarge this if possible. Maybe you can see it. But one of the things that it was given by the topic is called mathematics and quantum physics, trying to see what mathematics is actually is being used in quantum physics. So I was there at the talk of Cecil DeWitt Moret. That was in Kuala Lumpur, and she sort of regretted agreeing to this topic because when she looks the kind of mathematics that's being used in quantum physics, it almost included all the spectrum of mathematics that was already known. So that was the gist of the talk. In fact, she listed down the kind of topics being involved. And this brings me to the idea of this quantum theory, which is somewhere in the picture somewhere here. Today, it uses a lot of different things, things like logic. People talk about quantum logic. And there's this idea of categories that we had earlier. Categories are essentially a very general perspective of the mathematical patterns involved in mathematics. Okay, and quantum physics has now encroached into category theory, and people are using this to actually what you call apply category theory in such a way that they can program quantum computers. So, and of course, it has many other relationship, but this is the thing that sort of interests me at the moment. Okay, I have only a few students because we just started this. The person that was sort of introduced me to this particular topic is Bob Cooker, and we hope to do something along these lines in the future. So I think that's probably it. Thank you. So I guess I unshare this. Where do I do this?
There's a screen above there's a top there, there's an option, share something there, Thomas you can share something there,
Okay. Okay. I hope the talk is okay for you. Okay.
there's
Okay. Okay. Maybe I can open it. Uh, is the person referring to my old website? Is it? Well, okay. Uh, no. Uh, I have one website called QPhysics at some point in time, but no, the server was an old server, so the server has broken down. Okay, so uh, in order for me to bring it up, I will have to have another server. So that's essentially it. But those notes are essentially available uh, in soft copy if you want. But yeah, I mean it's just simple. Most of the notes are basically on quantum mechanics. So I'm not quite sure what the question really wants, but these are the things that are really perhaps one of the things that sort of differentiate theoretical physicists from even mathematical physicists for that matter. But what I'm saying is from mathematicians is that we tend to ignore certain details because we only are interested in certain tools, and these tools should make sense. So, for example, when you do, say, a fiber bundle theory, for example, okay, then there are certain aspects of the fundamental fiber bundle theory that you don't really need to actually describe the physics. So you have to have some kind of physical understanding of what you need, and then you try to see that whether the theory actually has it or not. Because if you go through uh, there is this idea of being rigorous sometimes may not give you more physical concepts, okay, may not give you the answers that you want to get from for the physics problem, but it does give you all the tiny details. So these are sometimes being ignored from the point of view of theoretical physics. But of course, these details can be very important. One of the examples is when you talk about solutions of Schrodinger equation, for example, then one has to be very concerned about what you call domain problems. So these are things that probably no, you have to know what you're asking and what you want. I don't have any.
I think we can see the question now. Is it? But I can see.
Yeah. Okay. Maybe, but maybe it's too small for me. Okay. Does that answer the question? Maybe the person can say something. Okay, more or less. All right. And then there was the second part. What's that?
As about such distinctive quality of the shape are elementals subjected to one institution, the way it used to solve is explored.
I think that is more from the first part question, right? There was another one. Oh no, it's different from that one. Such distinctive quality appreciation hardly matters. Well, again, it depends on what you want. For example, in the case as I mentioned about the domain problems, then if you simply apply the tools without properly understanding there are some boundary conditions that you need to satisfy, then they can actually cause a problem and the details matters. But there are problems for which the details might not matter. So these are things that perhaps you need to be able to judge whether details are of significant what you call. Sometimes we need the solution, but you don't need certain details of the solutions. Okay, so that's the kind of thing that. Well, there's no hard and fast rule. Okay, that all these things require some kind of experience and over time of what's needed for uh, for example, take the example of category theory. Bob was saying to me, "Oh, you don't need all some of the details. You just need these structures, and then you should be able to work out certain way of how the quantum computer making information flows." Okay, so these are no again it comes from experience rather than no, any rigid kind of procedure kind of thing.
We have another question. I think you can see the question in the chat box now.
It's just maybe I'll just open the chat so that's easier for me. Okay. Uh, which question is this? It was from Ilham, is it?
Which part of mathematical physics is the most important element to solve the complexity of quantum computing and quantum information storage?
Ooh. Uh, I wouldn't. Okay. Nowadays there are no. There are people who are actually because I'm not involved in looking at the complexity thing. Uh, but people are doing, for example, ZX calculus to actually optimize quantum circuits at the moment. And the idea of ZX calculus tells you that no certain computational problems that when that appears using Hilbert space will disappear because some of the things are no you have all this idea of like like doing a topological kind of transformation with respect to the information flow. So these are the things that probably would be helpful in a sense to understand the complexity. Because when you do in terms of Hilbert spaces, then no, the algebra can be very messy. But if you have a kind of what you call high level language, you know what essentially the what programming or what goals of the computing goals that you need, then you can actually engineer in such a way that the information flow is just flowing in this particular way. Okay, I hope that sort of answered it. I'm not an expert in that. Okay, I should have mentioned this at the beginning. No, I mentioned things certain. There are no mathematical physics is very wide, so I don't necessarily know all of them. Okay, so so computational complexity is one of it.
There's another question. Not alone by dynamics and chaos, chaos will like new and
Where is this? Let me just. Which one is that? What do you mean by non-indeterminate being related? Well, I mean, the subject of chaos probably appears sometimes if you the term chaos itself. I think it was what 1980s or something. So 1980s is considered relatively recent in a way, but if we talk about rather than the term chaos being used, then we talk about dynamical system. No, that existed much longer.
so the next question, in some extent, facts come after we have physical problems that cannot address. Example, Newton and calculus. While sometimes we have physics that come after we have understand maths. But this is not crucial. Physics. Yeah, kan.
Certainly, again, no, as I said, like what Greg Moore is trying to do, no, these are not really, how should I say, the common thing. Okay, to develop new maths ideas from physics. That is really very rare. I'm not talking about those old days. No, the current situation where we have already a wealth of mathematical tools, and then if you think of trying to create new maths from some physical problems, that probably it take quite intellectual capacity. Okay, because you already have tools. Okay, you already have a lot of tools, and some of those tools can address all the physical problems already. Okay, it's just like something like no, say something like the vector calculus. No, just to bring this thing down to a kind of level. Without vectors, for example, then you still can solve the problem. Meaning, what you have is essentially a couple differential equations. Okay, instead of vector calculus kind of thing. So there you can still solve the problem, but with vector calculus, then you find that, okay, this is going to be easier because I know certain properties of vector calculus to be in operation. Okay. And then one of the things that I read something that Witten wrote. No, not I wrote. I read something that Witten wrote. He was concerned about the idea of physics at strong coupling. Okay, so and he did this from during his graduate days until now. So most of the direction that he's trying to do is to make sure that he be able to describe physics at strong coupling, and that led to his methods that uses topology and things like that. And then we talk about duality. So if you do solutions on this part of the theory which has weak coupling, then you can. So these are things probably no. I don't know. I mean, it's a kind of fluke sometimes. No, it depends on a lot, and then how persistent are you pushing it. No, but there's no rule saying that okay, you have to have mathematics first and then physics, or physics first then mathematics. It really depends on the no, on how people push to solve problems. What? Okay, there's a question here. Well, I mean, perhaps not in a direct way. What people do essentially, I do not know this stuff too much. Okay, but the thing that, for example, Wheaton did was okay. Knots was previously classified using a kind of a two-dimensional version using knot polynomials. But what Wheaton did was to give it a three-dimensionality of the knots through Chern-Simons kind of. So he uses that, but that is not quite a physics problem. It's more of a maths problem. Chern-Simons do appear in physics, but the one that, as far as I know, okay, the ones that being addressed through the theory of Chern-Simons theory at that time, at least the ones I read, was only just to say that okay, I have this new tool that sort of give you a three-dimensional way of classifying knots. I'm not sure whether that answers it. As far as knot theory applications, I've not seen anything that sort of convinced me. The only thing that probably is the ones that I've tried to understand before, but no, I've not done any real research on it, was the idea of braiding problems. The braiding problems can actually tell you something about the physics because it talks about the quantum phases. So, and braids can be turned into knots. Okay. Yeah, maybe you can identify yourself first. Can you identify yourself first? Because I can't see anyone. Okay, all right. uh, if you ask me in the younger days, perhaps I would have some encouraging things. But okay, the idea is now we have a we have a problem in the sense that no, we are in competition with other groups, and being a small group, sort gives you a lot of disadvantages, particularly when theoretical physics is not really properly appreciated. So with a small group, then you cannot do much. So you need to ensure that there's enough critical mass so that the tradition. So my belief is always the tradition. See, the tradition. You do not want to have somebody very good, and then after he retires or she retires, then the tradition stops, and then you have to reinvent. No, it goes no go into the cycle again. And for in that case, people keep trying, always trying from the zero level, so it doesn't actually progress too much. So we need to have some kind of tradition. It doesn't matter what field it is. So if you have some kind of a tradition of say doing quantum computing or high energy physics, it has to move on. You cannot stay at the same level. That's my thought. Anyway, does that answer your question? Well, put it this way. Again, I always think in terms of tradition. If it's just if if you think doing say black holes will actually allows you to progress from say few individuals to scores of individuals, then I think it's a good thing to pursue. Okay, because we want that tradition to be alive. With respect to whether it's going to be useful, it depends on what you mean by useful. Okay, so these days, no, if you talk about quantum computers, then they say, "Oh, this is useful," but we do not really know because no, maybe quantum computing will be a flop. Okay, you will see quantum computing winter or something. Then no, it goes down. So again, it's hard to predict which one is more useful than another. But I would rather say this. It always brings me to the idea of what tools are you using. If you are using a tool in, say, in black hole physics that can be transferred to some other subject, I think that would be better. That's my answer at the moment. My involvement so far is I tend to use geometry, and I can be flexible enough. If okay, like quantization, geometric quantization is probably there's not much left things to do. But I started to think in terms of quantum information. Then I apply geometry over there. Okay. Yeah. May, sure, sure, sure. Yeah.
Professor, what do you think about applying machine learning in mathematics? Machine learning is the
Oh, okay. Right, right. I have no real opinions on that because I don't have enough experience and it does seem promising, of being able to do things with all this big data or something like that, or even looking at different things uh, one of the things that people try to do, for example, is uh, looking at some particle processes, things like that. But again, I do not know too much. But from what I know, the machine learning doesn't require too much of a sophisticated mathematics, as far as I know. I might be wrong. So if one wants to push that, I think that's probably a good thing to do. Is that Dr. Yun asking me?
Thank you, Professor. You have
Okay,
answered my
okay.
question. Thank you.
All right. Are you doing machine learning now?
I try because machine learning is relatively new in theoretical physics. It's a new tool, so there are some prospects in condensed matter physics, but not too much about the prospect of using a machine learning in other branch. There are only specific topics that you apply machine learning, especially in condensed matter physics.
All right. So I think it only uses some some linear algebra kind of thing, right? Or does it have any?
Actually, you use quantum Monte Carlo to generate a lot
Oh,
of data, then
okay.
apply machine learning to extract information from that data.
The
Basically, I think that's the approach.
okay. All right. Any other questions? And leave it to the organizers.
Is there anyone having question more? You can speak up, just turn on your mic. And for Kite Rider, for those students, the registration form is now left 1 minute. So quickly fill in and submit before 10 p.m. Okay.
Yeah.
I want to ask you a question regarding because as an undergraduate student, right? When we as a physics student, when we learn about mathematics, and then sometimes when we're introduced to mathematics textbook, they are quite rigorous. So sometimes we are a bit, or I'm a bit confused as to how much rigor do we need to get in, and then like for instance, if you compare between theoretical physicists, mathematical physicists, and let's say applied mathematicians who are working in the physics field, how much rigorous do we have to get in?
Again, it really depends on what one wants really. The rigor part usually, take for example things like trying to find a existence of solution, then you need to prove all sort of things. But sometimes existence of solution is not really required no, in a physical sense because the physical problem is the existence. Okay, so this kind of things sometimes you probably want to be a bit more flexible in terms of thinking of what you want. So maybe, yeah, go ahead. For me, I don't have any what you call hard and fast rule to consider what is better, what is not. When it comes to rigor, I tend to, okay, let's see if I understand the problem first. Okay, then if I need the rigor, then no, one goes for the rigor.
Okay, so let's say, for instance, because I'm also interested in the geometrical structure of like some physical situations of it, but I'm not that into quantum system. So let's say if I want to study the topological methods in fluid dynamics or fluid flow, then
Okay.
when we go to the rigors, do we need to go as deep as to like going into discerning the topological structure or the properties itself when we the research?
Yeah. Okay. The idea of using topological structures tend to focus on global ideas, global concepts. If the idea is just to do a kind of what you call put it this way, things there are certain things that requires topology, which is it's sort of doing things at a global scale. But if you are more concentrate to do numerics, then the topology can come later as a boundary condition or something like that. So again, to me, it's much more of knowing where to use topology and when not to use topology, because it's not necessary to have it all the time. Okay.
Hi everyone, still have questions? We will extend to 10, we will wait until 10, 10, 10, 10. Is it okay, doctor?
Okay, sure, no problem.
Wait for another 5 minutes.
Okay. So maybe
You have questions?
maybe I can ask people instead of people asking me that. So so how is USM theoretical group doing? I mean, what are they concentrating on? If I may ask.
Yeah, I can
Yeah,
Yeah,
sure.
I think the only very recent years, we have a few lecturers retired. Dr. Hong has retired, Dr. Rosie has retired, but we have new young people coming in. We have Dr. Su from came back from UK. He's an astrophysicist.
Okay.
And then we have Dr. Rosie who came back from UK as well. So he's really very theoretical quantum theorist as well.
Okay.
Then we have another young people. Dr. Low also is a quantum physicist. So we have, in addition to 2 person, we have now five theoretical physicists. But the problem is that we are working on diversified field. Not all of us are working together.
Yeah.
But I think Dr. Low and Dr. Hussein, they have more common interests. So I hope that they will be doing some joint project on common topics. But for the moment, our group has only 5 persons, very theoretical people, but our research project are not so much overlap. So that is the current situation.
Well,
At the moment, I'm going towards machine learning, that kind of direction.
okay. Well, 5 is greater than 3.
But the good thing is that we have a lot of interested students in theoretical physics. Every year we have new students. For experienced students, we're very happy because our students tend to be like interested in theoretical physics, and some of them are very brilliant. So
Okay,
we
that's
have
good.
sort of like continuous supply of new blood, new students. That's a good thing that I can tell of.
Okay, that's good. To me, probably another thing that I would I would love to see, more groups propping up elsewhere as well. Not just the main research universities. The younger universities might want to build up, because younger universities might have less constraint, kind of thing.
Okay, do anyone still have questions? Or Doctor, do you have questions?
I have a lot of questions, but
Okay, if nothing, then maybe we can end this meeting.
all right, okay. Thank you for having me.
Yeah. Okay, for our notice, we will upload the recorded video on our Faces Coffee Talk page. And yeah, I will try to get I already got the PDF file. I'll look there also. So anyone who want to review again, can go to our Facebook page. Okay. Thank you, Doctor, and thank you, Dr. Yun, for coming. And thank you, Dr. Shamudin, for giving us a chance to invite you. Thank you.
Okay.
And thank you for all every participant for coming tonight.
Thank you
See
for
you.
listening.
Thank you.
Okay.